There is a dominant assumption in Silicon Valley right now. If we just keep adding compute and parameters to a single neural network, we will inevitably produce artificial general intelligence. But pushing a single artifact to its limits eventually fractures under its own weight. Recent empirical data challenges this scaling assumption. A study published in Nature Communications evaluated frontier models on complex medical reasoning tasks. This chart shows the results. While pattern matching accuracy remains high, the model's confidence calibration plummets. The researchers found severe metacognitive deficiencies. The models frequently fail to recognize the limits of their own knowledge or handle unanswerable questions appropriately. The alternative to building one monolithic model is emergence, the principle that highly complex, coherent behavior arises from the interaction of simpler, specialized components. Physicist Philip W. Anderson outlined this in his classic paper, More is Different. He argued that knowing the individual parts of a system does not let you straightforwardly predict the whole, because higher levels of complexity demand entirely new explanatory concepts. General intelligence functions as a system-level property. Robust cognition relies on the integration of representations, memory systems, and planners, interacting parts that allow for continuous self-correction. We are already seeing the structural limits of the single model interface. The Stanford HAI AI Index tracks this trajectory, showing that frontier models are converging, with shrinking performance gaps across major traditional leaderboards. This clustering indicates that static test sets are saturating. To find the actual ceiling of current AI, researchers created dynamic benchmarks like GAI, which explicitly test multi-step execution and persistent tool use. This graph compares success rates and DIA's long-horizon assistant tasks. Humans complete these tasks 92% of the time. A frontier model equipped with plugins scores just 15%, struggling heavily to maintain persistent environment interaction. This failure stems from the long-standing symbol grounding problem. Systems trained strictly on linguistic form have no direct training signal for actual communicative intent or meaning. Without world-coupled semantics, relying purely on string prediction breaks down the longer a task runs. An LLM can guess the next logical word, but it cannot intrinsically anchor those words to physical reality or continuous time. Executing web workflows or debugging software requires persistent memory and continuous correction. That kind of long-horizon competence is an agent skill, demanding action and observation loops, not merely knowledge baked into static weights. To move past these limits, the engineering target must shift. Instead of training one giant brain that answers every query, we need to build a bundle of specialized competences. Cognitive scientist Marvin Minsky outlined this in his Society of Mind framework. He argued that the mind is built from many simple, distinct agents whose structured interactions yield intelligence. Modern AI already leverages this concept. Mixture of experts approaches explicitly route inputs through different specialized subnetworks, allowing systems to scale capacity efficiently without proportional compute costs. This diagram outlines a unified blueprint for agentic AGI. At the top, we have a literal society of specialized agents, independent modules for perception, retrieval, fast reflex skills, and deliberative reasoning. But a system of isolated experts creates a routing problem. How do these highly specialized modules share context and coordinate their actions without the entire process fragmenting? The solution maps to Bernard Baars' global workspace theory, positioning shared attention as the primary control mechanism. In engineering terms, this acts as a central data bus. Selected information is broadcast globally across the architecture, allowing separate modules to align on the current state. The Society of Agents supplies the specialized computational power, while the global workspace provides the shared context required to keep the entire system coordinated toward a single objective. Once the modules are communicating, the system faces a temporal problem. Robust reasoning requires distinct computational styles depending on the required effort. Psychologist Daniel Kahneman popularized this as dual process theory. Cognition is divided into a fast, automatic, heuristic mode, System 1, and a slower, capacity-limited, deliberative mode, System 2. DeepMind's AlphaGo provides a canonical proof of concept for this architecture operating successfully outside of language modeling. AlphaGo explicitly separated its control loop. It combined fast, learned policy networks with an explicit, slow Monte Carlo tree search, forcing learned models and deliberate search to cooperate. Looking back at the blueprint, we can map this dual process control directly onto the architecture, establishing separate fast and slow pathways to action. Current LLM pipelines are beginning to implement this. Multi-agent debate and explicit verifier pipelines force the system into a slow loop, where diverse models critique and check each other's work before acting. True autonomy demands separating the generator from the verifier. Without a slow loop to simulate and check logic, fast pattern matching inevitably drifts into hallucination. This structural separation brings us back to the frontier models failing at medical reasoning. Their inability to recognize their own limits is a complete lack of metacognition. John H. Flavell defined metacognition as the active monitoring and regulation of your own cognitive trajectory, knowing how well your reasoning is actually going. Translated into software, this requires a dedicated supervisor module. It must monitor progress, detect failures, and dynamically reallocate resources under uncertainty. Here is the final component of the architecture. Metacognition governs the entire loop, maintaining oversight connections that monitor the global workspace, the dual process pathways, and the memory systems. When tested on complex coding benchmarks like SwebBench, agents utilizing this kind of careful orchestration and tool-driven workflow consistently outperform single-shot models. Implementing this oversight is not free. Multi-agent workflows introduce strict cost and accuracy trade-offs, massively scaling token consumption and coordination overhead as conversations lengthen. Ultimately, AGI-grade robustness effectively lives within the coordination loops between specialized models, external tools, and long-term memory systems. This diagram illustrates the AGI stack, demonstrating how intelligence capabilities compounding vertically. Layer 0 contains foundation models for pattern learning. Layer 1 adds tools and memory. Layer 2 introduces multi-agent protocols. Layer 3 integrates the workspace, dual process loops, and metacognitive oversight. Richard Sutton's famous bitter lesson states that general method scaling with computation will eventually beat handcrafted knowledge. But this advocates for scaling primitives like search and learning, not necessarily a single monolithic network. Externalizing search into distinct processes like planning, debate, and tool exploration at Layer 3 aligns perfectly with the true meaning of the bitter lesson. Robust autonomy, safety constraints, and self-evaluation are architectural behaviors. They live naturally at the orchestration layer and cannot simply be baked into the foundation weights at Layer 0. Even with a flawless Layer 3 cognitive architecture, the system remains incomplete. To reach emergent general intelligence at Layer 4, it needs environmental grounding. Roboticist Rodney Brooks argued for intelligence without representation. He maintained that building complete intelligent systems requires tightly coupling them to physical perception and action. These physical and motivational drives are represented here by the external inputs feeding into the architecture: embodiment, motivation, and learning from interaction. Without intrinsic motivation or a persistent drive for curiosity, LLM agents operate as stateless, amnesic describers between episodes, incapable of choosing what to explore next. Proofs of concept like the Voyager agent in Minecraft demonstrate that embodied, open-ended learning works. The agent writes its own code to explore and build, but it requires massive iterative feedback and verification loops to succeed. As shown by recent testing on benchmarks like Lifelong Agent Bench, current LLM agents still fail to accumulate and transfer knowledge over long periods, getting bogged down by irrelevant context. Scaling complex agent architectures, built on specialization, interaction protocols, and self-monitoring, provides the structural framework for AGI-like robustness to emerge. Cognition is a stable society of systems.